You all right with recording? Are you all right with recording? Okay. We didn't get around to doing like whatever waiver, so I'm just asking people. Yeah.
What's up? No, this webcam bootleg.
Oh yeah, I didn't see this. You can if you want. That's probably the original plan, but I would say I just have left. So okay, we'll do both. We did it with ApacheCon, and that thing actually does a fairly good job. But yeah, you'll probably get better. What are you doing for lunch? I was talking to Steve Blackman, and well, they like swamped people who asked that project for they were having some questions about the demo stuff, and since I'm just sort of making up as I go through it, you're kind of really actually yeah, this is stuff like how do they do a release because they're a Python project, yeah, like and like I know it can be done, but I don't know if there's like other means you make rules that like what's up? On that one. It's not on this one. Let me go to that comes down and see if I can get that.
They got someone coming down supposedly. So
Just one thing. There must be some tech there. Well, that's actually how he wants to do it. When we were all discussing room sizes, oh yeah, this looks a lot bigger than what was planned. They were do the manual section. As they switch the wires. Ah, wait, this one is 3 here. So this one is that one down there. This one is 2. Nope. Oh, no, please. Oh, it doesn't right. No, please. That's one of these values. No, it's not. Well, it's not that long. Yeah. No, but this one is the one. So Roman is sort of landing at the level of rock. Really, really great. All right, thanks for that. There you go. See, that's what I do.
that's on your computer then. That's
That framework looks familiar. You have separate screens now? Yeah, I could, but as soon as I that applies last time.
what's up?
Okay, so that's recorded with this one. Looking around, I can't see any so they're probably just yeah.
Come down the front, people. We have no mic. If I have to shout at you, I'm going to have to, my voice is going to disappear and Chris is going to have to give my talk.
Yeah.
And he doesn't like giving my talks.
Oh, come on. I think it's probably just not planned. So maybe But if they were speakers or they weren't, yeah, you just did it. Well, they're going to be sending someone down to fix the mistakes. So it may show up in the master. They can pick it up like that. Yeah, basically.
No, that's the same. Isn't that correct?
What? I'm thinking of the master. No, I've been doing the same setup for years. Are you okay with the color?
Well, I just tried to get it up.
Ready to start?
Everyone, if you can come down the front here, because we don't actually have a microphone, and I don't want to shout at you.
Yeah, I don't care if you want, you can. All right. Welcome everyone to ApacheCon North America, the IoT track. My name is Trevor, and you don't have a mic, so if you're speaking, get ready to project your voice, and thank you for all moving up toward the front so we don't have to yell at you. Without further ado, go through the theme and how to have fun, how to become an IoT developer and have fun.
Hi, thanks everyone for coming along to this talk on how to be an IoT developer and have fun. I'm just going to show of hands. Who here sort of works in IoT? Are you having fun?
Yeah.
Good. What are you doing at this talk? You already know what I'm going to say. Anyway, just a brief introduction for who I am. I'm a freelance developer. I've worked for myself for more than 25 years. I'm currently the VP of the incubator and Apache IoT, which is a real-time operating system. After this talk in the same room, I'm going to be giving another talk on Apache IoT. So if you want to go on with that, then more than welcome to stay. I've mentored a whole lot of projects at Apache. I'm involved in a whole lot of PMCs as well. I also founded about 5 years ago the IoT Link in Sydney, Australia. We're coming up to our probably 70 meeting or something like that. Yeah, for a while. And I occasionally run IoT workshops. I also teach high school kids how to do electronics and stuff. Good fun. So just going back a little further, how I actually got here. Because I've been programming for so long, I actually started out doing fairly low-level stuff. One of my first jobs I had was a TV election broadcast system. So that involved lots of low-level hardware. You had to synchronize it all in real time. And, because we kind of broadcast live on TV, stuff up. So that was sort of my introduction. And I worked in that field for a number of years until I started working on a telephone exchange. And at that point, I thought, this stuff is actually quite difficult, and maybe I want to do something else. And that was just when the internet thing was coming along. So I thought, this is quite fun, and I jumped ships and started working on that. And after a few years of doing that, this thing called open source hardware appeared. Open source hardware is a little bit different than open source software, but some of the principles are the same. And I got interested in that. So I was sort of thinking, I wonder what has changed in this space over those years. And it turned out that it actually changed quite a lot. So I got interested in that, and I mostly just spoke at conferences on it, just with a hobby rather than my and then I started getting work in this field as well. And more recently, I've come back to working on hardware and actually doing stuff in C, which is the same as what I was doing like 25 minutes ago. Nothing changes really. But it does. Things have changed. It used to be that hardware was really expensive, and it was very difficult to program. If anyone is of my age and has been programming 25 years ago, you probably knew that you had to physically take the chips out of the board, erase them with ultraviolet light, put them in a program them at some time, and then put them back in a physical device, and maybe you would work. So we now have low-cost, easy to program hardware. You plug in a USB port, upload the file to it. Sometimes you can just upload the file over the air by Wi-Fi. We have the hardware is a lot cheaper, and it has a lot more memory, so it's not a constraint. We also have, I'll say, modern development tools. It's a relative term. It's improved. And there's also some other things that have happened in terms of standardization and the whole open source becoming involved in open source hardware, open source software. You can get, if you need to do something that's quite often now that there's an open source library out there that you can do it, it used to be that you have to actually buy a lot of software. That point, you should probably go along to Chris's talk, which is in the front row here on PLC stuff. Oh, okay. So he is after my review talk. If you want to hear about what's happening in the industrial IoT space, go on to Chris's talk. So you may have heard that hardware is hard. It's pretty hard to, once you've made a board and shipped it out there, to actually physically change that. You can't just send an update over there. If there's something wrong with the circuit, or something wrong with the board itself, then there's not much you can do. So the people who are coming in a little late, just come down the front if we don't have any mics. I don't want to have to yell at you all. You definitely, like, everyone here's been on a software project that's running code, I'm sure. Hands up. Right. Estimation in software is hard. Right. Estimation writing software and hardware is even harder. Things just go wrong, and unexpected things happen, and it's going to take you a lot longer to develop the firmware that runs on the hardware than you think. It's hard to debug and find errors. I'm going to go through a couple of strategies of how to do that. And one of the hardest things to get right is over-the-air updates. How do you actually update your software on these devices? Whoops. W went disappeared. So you want to become an IoT developer. So I asked for a show of hands before, and there's a few people who are already working in the IoT field. Now, it's actually changed a bit in the last few years, and there's basically, there's no real such thing as an IoT developer. It's no longer a niche thing. It's part of a job in another field, really, is what it comes down to. So you could be a mobile phone developer and have to collate and display data that's collected from IoT devices. You might be a big data programmer and you need to collect data and make sense of that. So it's touching on a lot of different careers, and it's becoming much more important. So, but I'm going to assume that we're starting off from scratch and that you want to be more involved in the hardware side of things. My first advice is play toys. You can learn an awful lot by just getting a little bit of hardware and playing around with it. And this hardware is now cheap and easily available. There are platforms like Arduino and Raspberry Pi and others as well. So just grab one of those, and it's always best to have a project that you have in mind, what you want to do, and do something like that. Like if you like brewing beer, hook up a little temperature sensor with an Arduino and measure what the temperature of your beer is at the time. Good. That might tell you something. If you've got a green thumb, then do something with plants. Measure the moisture in the soil or something like that. So often having a project or goal in mind will get you to play around with it and make you a little more enthusiastic about learning. For people who don't know, this is the Arduino board. This is quite an old one. The form factors of the sort of prototyping boards like this haven't changed much over the years, but more modern Arduino boards are smaller form factor and are much more powerful. Well, the reason why I like the ones with the original chips in them is that in the case of damage the chip, you can pull it out. In 15 years, I've never damaged the chip. So, anyway, but I told that. This is the Arduino IDE. What I like about it is it's really simple. Like, it's only got a few buttons. It's area where you write some code in it. It's certainly not intelligent or Eclipse, but it works and does the job. The buttons up the top there are basically verify my code, upload my code, and the one on the very end is a serial debugger. That's basically it. So just say that you don't have access to this hardware. You've got almost everyone here has a mobile phone, and your mobile phone has a lot of sensors in it, and it also has a lot of ways of communicating with other devices. Bluetooth is a really popular one. NFC is another one. So you can just start straight away by getting your phone out and having a bit of play with that. Everyone staying at the hotel here? This is probably an NFC card. You could probably do something with this. So it's sort of fun. Play around with it. And you can get NFC stuff really cheap. You can get stickers, business cards, prepaid polls, you name it. Like, it's just about everywhere. I actually know I came through an airport the other day and I noticed the luggage tag actually had an NFC sticker on it. So, and there's some specialized hardware as well. I quite like these devices. These are called Rubies. And it's a disc about this big. It's got a coin battery in the middle, very low power. If you do things right back in the last 6 months of the year, you can make it as a little Paprika logo or something like that. It will actually run ApacheCon as well, so you can put a real operating system on it and do more interesting things with it. And the range of Bluetooth on that is 100 meters, 300 feet, up to 500 meters, so it's got quite a range on it. Really interesting device. So the other thing to do is learn a little bit about electronics. You don't have to be an expert at it, but just start doing the basics. So, create a simple circuit. Get yourself a breadboard with wires, a few LEDs is probably the first thing you want to do, make a little Linky program, and do that. So, depending on how you wire stuff up, it may not look pretty. There seems to be two styles of breadboards, one where you put all the wires flat, and that's nice and neat, and one where you make a nest of wires like I do. So, you can, use up that. But just to get the basics going, it turns out there's a few companies these days that are actually they get basically the latest chips and they put them on a little breakout board for you, and they usually put some sort of interface on there and the other components that you need, so you can just hook it up and go with it. And there's a lot of pre-assembled boards that you can get very cheaply, and they're very easy to use. They usually have a standard interface like I2C or SPI. You can basically think of them as Lego bricks, and you can just plug all these bits together and connect them all up. And you can very, very easily make a working prototype. I'm not wearing it today, but there's a smartwatch manufacturer called Pebble. Unfortunately, it's bought by Fitbit and no longer exists. But if you do a bit of hunting around, the original prototype for that watch was the guts of an old Nokia phone and an Arduino. Right? So you can get playing around with this stuff, you can very, very quickly make a prototype and get something working, and then you can refine it. So here's a little example breakout board. There's a little air quality sensor. Very easy to use, straight up to Arduino. And as I said, you can sort of chain a whole lot of boards together. This here this is a pressure and humidity sensor, a temperature sensor, a light sensor, and a sound sensor. So this is like an environmental device prototype. And like you can see there, there's no extra components that are required. This is an Arduino compatible board with Wi-Fi on it. It's very easy to hook up, put together, and you can get something working very, very, very quickly. Next step is learn how to solve it. It's easier than you think, particularly if you start off with larger components that are through-hole components. Sometimes these are getting a little harder to get. They can be a little more expensive, but not much. And this is, one of the best things you can learn is by making mistakes. And when you start out with solving, you'll make a lot of mistakes. Right? So learning the techniques of how to correct those is actually more important than doing it perfectly. One thing I found that helped me a lot was using a flux pen. So you can get the pens that are filled with flux on the board where you want the solder to go, it won't go anywhere else. That's good. Solder braid, which is like copper braid, you can put on the solder, heat it up, and whip away the solder. It's good for correcting mistakes, and you will make mistakes in those. It's good fun. So once we have a look at that prototype before, there, record here, and then we can take that and we can turn it into something like this. This is a little more permanent. It's it's a bit neater. It's still not probably professional. So taking aside from that, you want to probably go back and learn a new language. Who here knows C? You started off with C. There's probably a few hands, but I would guess not the whole audience. C is considered not a modern language, even though it does actually have a lot of modern features. And C has actually changed quite a bit recently. I'll show you. These days you can get boards that will run Python, Go, PHP directly on them. There are some good points to that and some bad points to that. But C is probably one of the most common languages that are around. Chris asked what was a good point to have PHP running on. The answer is there's no memory management and that it's actually quite robust. So if you write it, it's less likely to crash. It does have its place. You may need to forget what you know if you're an old school C programmer. And if you use it, it's not as complicated as you think. And the style of it and how you write C has changed a little bit. So here's a little example. This is just a very simple code for Arduino to make a LED blink. But there's something in this program that you're probably being told never to do. Does anyone want to take a guess at what it is? Global variables is probably one of them. Yeah, with small, simple programs, you tend to use a lot of global variables. It's not going to kill you. Fine, but there's one other obvious thing there. Maybe it's not so obvious because you can't see the underlying code there. It's actually this loop here. This loop is an endless loop. So you're always told don't write endless loops. Well, programming these sort of devices, you won't often write endless loops. You want things to run forever. You want them to wake up when they need to and do something and then get back to something. So often a lot of code is based on just writing at a lower level than what we had previously. I suggest go back and read this book. You probably had a look at this at university. But there's also more modern books on C. This one in particular I recommend. It's quite good. So C has actually improved a lot. There's several standards. I think there's a new one that's just come out actually. So there's C89, C99, C11, and I think there's C18 standard. It has a lot of new useful features. It has some more types like booleans and ints, auto sizing of arrays, has floating point numbers, inline functions. So it is a little different to how you may have done it in the past. It's
Not either. They're not as standard, is my understanding. I think I wrote to see compiler. Now, there's some hardware.
Oh, there's hardware that definitely did it for that. Yeah, that's
Nothing.
Yeah. Okay. I'll look at that. So you can do an awful lot in a small amount of code. On a Arduino, for example, you can write a web server in about 20 lines of code, and it compiles down to about 2 days. You're not going to be serving videos and huge images with that. You can make it respond to the simple requests and do, basic XML or whatever the format you like. And you can also, there's another good example of doing a lot with a small amount of code. Yeah, if you have a look at this formula here, it's a simple function. It takes an integer, which is t for time, and it returns a number based on some bit shifting of time. It's actually called a generative formula, and this one in particular is a little interesting because it takes advantage of a few things that you probably wouldn't normally do. This deliberately overflows, right? Because you can look there, depending on what you put in the shifts. As soon as t hits, even slightly large, it's going to overflow. What this does is actually you can think of it as it's like a pseudo-random number generator, but it has patterns. So the human brain doesn't really like total randomness, but it likes things to be a little random, but it likes repetition in there. You can use this to make patterns with blinking lights or even sound. This will make electronic music just by putting in the right bits. Not particularly good electronic music, but it's an interesting little thing. You want to know some electronic basics, so play around with the fact that voltage and as the equivalent digital. So 5 volts is 1, 3.5 volts is 1, depending on what your voltage your board runs on, and 0 volts is generally 0. It's not precise, it's a bit of a fuzzy area there. Useful things to know is, if you're playing with LEDs, how do you limit the current? How do you use transistors for switching? Using capacitors filtering, so your circuit works well. Pull up and pull down resistors are often useful when using switches and things like that, and voltage dividers as well for hooking up sensors or for a simple way of getting the right voltage that you need. So all this is pretty straightforward stuff, and there's lots of information out there on the internet. So what else? The other thing that's changed in recent time is that it's now really easy to make boards. It used to be 10, 15 years ago that making a board would actually cost thousands of dollars. These days you can create a board for a few dollars. I think the last one I ordered was 10 boards for $5, and that included the postage. So, and they're easy to make. So there are a lot of open source programs to make and lay out boards, and they vary in complexity. KiCad is probably the one that you've mostly run into, I would guess. Anyone? Show of hands. Anyone heard of that? KiCad? No? Oh, wow. Okay. How
do you spell the name?
KiCad. K-I-C-A-D. It's probably the leading, more professional version. What I'd recommend is starting out as a program called Fritzing. It's very simple, it's visual, it's drop and drag, it has a breadboard view and a PCB view. It's actually quite nice to work with. And it also has a few checks in there as well, so if you do something that is not quite right, it will tell you about it. It's not perfect, but it's decent, and I think it's a good starting point to go with. One thing when you're starting out with this, the temptation is to buy lots of cheap stuff off eBay. Right? There's nothing wrong with that. It's cheap. It will mostly work. However, it probably doesn't come with a data sheet. So you don't really know what you're getting
and in some cases that's going to be more important. Some sample circuits that you can learn from, and so forth. And if you're talking about some things, they also can include important timing information, and at some low-level stuff with some protocols. The Arduinos and other chips are fast enough to do what's called bit banging, where you can just basically manually do the protocol, just a whole lot of turning digital lines on and off and a little bit of timing information in there, which can be quite useful. So the datasheet will often have a circuit diagram on it, so you probably need to start learning how to read those. Just know some of the basic symbols and how to match up pins on the IC is a good start. So here's a nice schematic here. This is for a accelerometer. Just have a look here. Yeah, anyway, so you can see that this is how it's hooked up. It's got a couple of capacitors, a resistor there. Hasn't got too many other components in there. There's actually an error in there, I've just noticed. That's all right. So I was talking about fritzing before. Very easy to use. And one of the best things is that it'll actually export the files in the proper format. It's called Gerber format, that you just pick them up and send them off to get made to a real PCB. And it's handles surface mount and through-hole components. It comes with a decent library of footprints, and this is when you're starting out, is what you're going to need. So each component has its own physical shape and size. There are a whole lot of standard shapes and sizes. There's lots of components that are not standard. And often with other programs, you have to actually make the footprints yourself, and you have to spend a lot of time doing that. So this comes with a whole lot of things. It also has a whole lot of libraries for some of the commercial manufacturers of the breakout boards that I was showing before. So that can be very helpful as well. It has a few issues. The breadboard view is not as compact as you'd like. So here's an example of just showing the interface. You can see that it's drop and drag. You can hook up the wires in a board view. As you're making changes on this breadboard view here, it's going to also update the schematic and the PCB views at the same time. So here's what PCB view would look like. You can see it has the same LEDs and resistors on there, and where to place them and so forth. And then you can just go export. That'll export a whole lot of files that are in the right format, which I said is a Gerber format, and you can ship that off, and then you can get a board sent back to you like this. So, and that is really easy to do. And it can make really complex boards. It's not just simple boards like the one I showed you here. So here's quite a good. And it can make really complex boards. It's not just simple boards like the one I showed you here. So here's quite a complex one. It has some limitations, as I said. It'll only do 2-layer boards, so it's not going to do more than that. But for most purposes, when you're starting out, that's fine. And hopefully, when you solve everything up, it works. So it's always good. So some other things to be aware of. What happened there? Anyway, so don't go too small too quickly. But there is a temptation to use surface mount components like they're cheap. They will do everything, but it may mean that the prototype that you make is really hard to debug. On both from a software point of view and from a physical hardware point of view. And it also makes it hard to make modifications to the board. I was involved with a project where one of the chips had been wired up incorrectly, and if it was on a larger format, we could probably just solder a wire on the board between 2 pins, and that would have fixed the problem. But because it was surface mount, it turned out that the track that we needed to solder to was actually underneath the chip. So someone got a microscope out, tried to drill in from the back of the board to see if they could fix it that way. It didn't happen. So don't go too small too quickly. So it makes it hard. And it also, the boards, when you're first starting out making boards, it may have a few mistakes. And so you'll send off the 10 boards, you get the 10 boards back, there's going to be some defects and some problems there. So yeah, but we also had one case where we had boards where they basically make a solder stencil up, and they make 20 boards at a time because they're tiny, they're only this big, and someone had copied and pasted. They positioned one board and then copied and pasted to make the rest for the solder mask, and in one of the copy and pastes they missed a layer. So we actually had one board in 12 or whatever it was that didn't work because of a copy and paste error. Not good. So you want to actually test the hardware. So you want to have some way of testing the hardware itself on the board. So you want to have like some little points that you can check for things. You might want to have a self-test on the board itself when it starts out. It sort of goes through a little check routine and make sure that it's working, and then it gives you some indication of doing that. That will save you a huge amount of time. If you're making a lot of boards, actually making a physical test rig to put the boards in and test them is also a good idea. The other way to test the hardware is to not actually use it at all. Because writing this code and then uploading it to the board and then seeing if it works on the board, that all takes time and effort. So quite often, it's better just to write your code in C and test it on your computer. It's actually quite easy to do, and it's much more productive and has a much faster cycle time. Standard C works just about everywhere, so it work on there. So some of the hardware platforms have simulators, so you can actually simulate real things happening on them. If they don't have simulators, then you can mock that. You can. There's ways around it. So about 90% of your testing you can actually do on your computer, and then the final 10% you can do on your hardware. You may have to stub out some few things that are hardware dependent, but that's easy. But eventually you do have to test it on the real hardware. I certainly wouldn't ship without testing it on the target board, because you don't know what's going to go wrong. And most platforms do have modern IDEs, so you can set breakpoints, you can step through the code, you can look at variables and so forth. So that's a great leap forward over what we used to have to do. The problem I've run into a few times is that you'll test something in debug and it works fine, and then you'll make the